All right, good afternoon, everybody. Everybody's all ready to go? Super excited? Not quite, right? Maybe. Everybody have a nice Thanksgiving? Yeah. So we got, what, 2.5 weeks and then finals, right? Pretty much. Yeah. It's going to go fast, right? um, you're working on some homework in here for Friday, right? Will be. See, I thought everybody would be, they took advantage of Thanksgiving break and had it all done and take advantage of it for other purposes. Yes. Yeah, that's a good thing to do. But we do have some homework that's due this Friday, so don't forget that. I think I'll have one more homework assignment. Looks like I'll give that to you on Wednesday. Probably be due. Trying to decide on that. It'll either be due a week from Friday, or possibly that following Monday. We'll see. Trying to work out some things, scheduling for myself and for this class, in terms of how to work with France. The issue becomes, you were at France, right?
Yes.
So you take finals early.
Yeah, you do.
Yeah, so you start finals right during that last week.
You just turn them on Monday instead of on Friday.
Yeah, because you're done by that Friday with everything. Yeah. So for this class, I'm trying to figure out how to make that all work. That may mean that certainly the last day of class, we're not going to really do anything other than maybe course evaluations, because that's a Wednesday, and they're already in the middle of finals that day. Monday is a little bit iffy even yet too, so we'll see. We may go Monday and maybe Wednesday. We'll just do course evaluations or something like that. Trying to work that out in our schedule to see how that all fits with everything. So that's kind of where I'm at. I've been trying to figure this out. I think what we're going to do is we'll do a little bit more with absorption today, kind of wrap it up, and probably start in on the next chapter, which I just realized I didn't put out the slides for you for the next chapter either, so I probably need to do that here. May have to take a break and actually do that here. So let's go ahead and wrap up chapter 12, and then I'll put some slides out there for you for 13, and then we'll jump into 13. So that's the game plan for today. I think last time, it was a while ago, right? A little over a week ago or so, we were doing some sizing on absorbers and strippers. It applies to either one. So let's go into that for the time being. And I think this is where we ended up looking at how to size one of these columns. I have a couple of other topics I want to deal with in this chapter, and I also want to show you how to maybe approach one of these problems using something like ChemSep. Okay. So let's go ahead and finish out the slides, and then we'll take a look at ChemSep, and then we'll jump into chapter 13 then. Okay, so, all right. What we haven't talked about in here yet is how do we deal with absorbers and strippers in which there's more than one solute. And it gets us kind of back to where we were with distillation, right? We worked our way up to the point where we got to possibilities where we were considering these multi-component systems. So the simplest way of handling these kinds of problems are ones in which the solutes are all dilute. And so when we have a problem like that, we can make several assumptions. Some of these are going to be the same assumptions we've been making all along, and then we'll make one additional one here. So to handle these types of problems, first off, we'll start with, and we'll assume that the carrier gas is insoluble, right? We've been assuming that all along. We've been assuming that the solvent is non-volatile. We're assuming that our system is at constant temperature and pressure. We've neglected any kind of heat absorption, and we've assumed constant flow rates. The last assumption that we'll make to at least treat these dilute multi-solute problems is to assume that the solutes are all independent of each other. So what that means is that the concentration of one solute doesn't depend in any way upon the concentrations of the other solutes. So if we do that, then it allows us to treat this absorption problem as if each solute is a separate entity. So let's consider what this might look like, right? So here's, let's say, a column that we have set up. We have our usual, so I get my pen working here. We have some sort of solvent coming in. We have a gas stream, let's say, that's going in. We're exchanging, right, mass transfer with the solute between those two streams, and so on. And so then we would have coming out the top, we would have obviously another gas stream. Coming out the bottom, we'd have another liquid stream. And if we had, let's say, more than one solute, let's say in this case maybe we had maybe up to maybe 3 of them, for instance, as shown here, then we're going to have to consider the relative amounts of each of those 3 solutes in each of the streams, right? If we can make this assumption that they're all independent, then again, we can treat each solute separately, and that kind of simplifies this greatly for us. And so what that effectively means is the following. When we do a problem like this, oftentimes at least one of your components is specified to have a value in the, let's say, the outgoing vapor stream, gas stream. The other ones may not. You may know what they are coming in, but you don't know what they are going out. As long as we have one that we know that's going out, then we can go ahead, solve the problem with that particular component. That would enable us to determine things like the number of stages that would be required to carry out that separation. Okay? And then once we've done that, then we're going to go to the next step. We're going to take a look at the other solutes. Okay, so here's the general scheme. Let's suppose that you know the outlet solute concentration for, let's say, component B. Right? Considering maybe a 3-component system, A, B, and C. So for component B. That means that the problem is really specified for solute B. And we know how to solve that, right? We could pretend that it's simply a standard problem that we've been working on. That means that we could go and we could set up a McCabe-Thiele type plot. We could determine the number of stages. Stages, I got a typo there. Stages. We're going to assume each is dilute. We'll have maybe equilibrium lines that are probably going to be linear. Operating lines may be the same. So then we can use our McCabe-Thiele plot to step off stages, for instance, right? We can calculate an operating line as we've typically done, right, based upon L over V values, which we've assumed are constant in this case. And so we can work it all out. We can figure out how many stages do we need to accomplish this separation for solute B. Well, that's fine. Now the question becomes is, what do we do with the other solutes? That becomes a little bit trickier here. What we sometimes end up doing then is the following. We know that we have one piece of equipment. And that means that the number of stages that we need or are required based upon the information that we have for solute B have to be the same for both A and C, our other two solutes. So in order to do the rest of the evaluation, oftentimes then we need some sort of a trial and error solution to figure this out. So what does that mean? Well, for us, that may mean, let's say that we pick, let's say one of our other two solutes. We're going to guess a value for, let's say, y1 for one of these other two solids. So let's go back and look at our plot here. So we're going to guess a y1 value up here, okay, for instance. And then what we're going to have to do is we will then step off stages on a McCabe-Thiele plot. And we're going to see if that would then agree with what we know about y a n plus 1 is. And if it doesn't, then we're going to have to re-guess and start over again and step our way through it. Because we know the number of stages, right? The number of stages is fixed. What we don't know is that value for y1 that's going out. So you can do that for both solutes, and once you've done that, then you've completely solved the problem. Okay, and so it's relatively straightforward, relatively easy, as long as we have these systems in which we can assume that everything is dilute and that the solutes act independently. All right, so let me pause here for a moment. Any questions about multi-solute problems or anything that we'd have? Pretty straightforward, I think, once we know how to do it for just a single solute. Okay. All right. So what should we do next? Let's take a look at how we could solve one of these problems using something like ChemSep. Okay. So to do that, what I want to do is I want to go back. Let's go back to the first example that we did in this chapter. We did an example here where we had air that contains some chloroform, and we want to absorb the chloroform with pure water. Okay, so we've already worked out this problem. So just to kind of remind ourselves what we have here, right? So we've got water coming in the top. It's our solvent. It's pure water. We have a feed gas coming in that's air plus chloroform. We have treated air coming out the top. It has a very much reduced amount of chloroform in it, and we've picked up some chloroform into the water, right? And so in solving this problem, we went through the whole analysis, and we determined, obviously after figuring out the equilibrium line, figuring out an equilibrium constant here, right? We had an equilibrium constant that was based upon our Henry's law constant and pressures. That gave us an equilibrium line. We figured out the operating line for this particular problem. And with that, then we constructed a McCabe-Thiele type plot. And we figured out that we needed something a little over 4 stages in order to accomplish this. Okay. somewhere around 4 point something, 4.4, 4 point something, for the number of stages. Okay. All right. So let's take this problem and let's try to put it into ChemSep. Okay. So I need to jump out of here, and let's launch ChemSep. Okay, so starting off to do the ChemSep problem, all right, we have 3 components that we're dealing with. We have air, chloroform, and water, right? So we should go ahead and enter those as our components. Right, we can use find to add them in and so on. So we get 3 in there. And then we need to go to operation. So when we go to operation, it's going to be an equilibrium type column. In this case, now, when we go to the configuration part, instead of this being a distillation type problem, we're going to call it a simple absorber stripper type problem. Now, again, when we use simulation software, we have to know in advance the number of stages that we want to use. For this problem, we know that we need something like 4 or 5. We're going to try both today. So let's start with trying, let's say, 4. So let me flip my screen around here so I can type a little bit. So let's say that we needed 4. We know that we needed a little bit over 4. Okay. So once you set this up with 4 stages, it's going to suggest for a simple problem here that we're going to be feeding on 2 locations. And the location should be stage 1 and stage 4. Which makes sense, right? Because when we have an absorber, right, we're feeding say a liquid in the top, or feeding vapor in the bottom, right? And then we still have the bottom and top stream coming out as well. All right. Next thing that we need to do then is we need to think about properties. Now this is a tricky one. I think you'll find sometimes, depending upon what your components are, the tricky part is the thermodynamics a lot of times, knowing what's good, what's appropriate. In our problem, the original problem, right, so we had chloroform and air. What did we assume in that problem? Before we set us up here and I show you what we're going to do with it, what did we assume about it? What were our assumptions when we solved the problem? Could the air go into the water? Could the water go into the air? What have we been assuming in a lot of these problems? Non-volatile liquid solvents, right? So that means water is not going into the air, right? Okay. So then the only thing that we have that's undergoing mass transfer is essentially the chloroform, right? Going from the air to the water. Now, in a real system, depending upon what your air feed is going in, it may not be saturated with water. So if it wasn't saturated with water, in the absorber, you would have water transferring into the air. Likewise, there is a certain amount of air that can go into water as well, right? To try to mimic what we did in our example problem, and for lack of some really good thermodynamic properties, you can sometimes find some, what I think we should do to start with is we're going to set this up. We need a K value. And you know, we've been using things like Raoult's law, we've been using Dykema and then picking other things and so on. We're going to choose, in this case, polynomial K. Okay, so what does polynomial K do for us? Polynomial K essentially gives us this equilibrium constant. And it's written out as a function of, say, something like temperature. And they write it out in a polynomial form. So the exact form of this that's actually part of ChemSep looks something like the following. I'm going to describe it to you. I don't know where I can write it, because I don't really have anything up to write it on exactly here on the screen. So let me just kind of talk you through it. I'm trying to avoid using the board as usual, right? Okay, it makes it tough sometimes for me. It goes something like this. It says that K raised to the 1 over m power is equal to A plus B times T plus C times T squared plus D times T cubed plus E times T to the fourth. Okay? That's the polynomial form that it uses. So as soon as you select polynomial K value, what should pop up in this lower part of the window is something that looks like the following here. Right, so you've got A values, B values, C, D, E, and you've got M, right, for each of your components. What we know from our problem is this equilibrium constant for the chloroform, right? And it had a value, if you look back in your notes, of 105.5.
We're not getting the parameters to load.
I know, you're going to have to enter them.
Oh, okay.
We haven't gotten that far. Mine's already done, all right? I'm getting to the point where we're going to explain what these are and why we're going to put them in, okay? So we know a K value, and we calculated a K value based upon Henry's law for our particular problem. And we saw that it had a value of 105.5. We're operating our absorber at constant temperature and pressure, right? So I don't care what the temperature dependence is. All I want is a value for that, correct? In this problem, right? So as long as we put it in there for the conditions that we're operating at, we don't need to have the temperature and pressure dependence, because we're not allowing for any changes in that, right? We're not allowing for any heat absorption or anything like that. Okay? So that means then that for the chloroform, we want a K value of 105.5. Well, that would be the constant value, the A sub I. So if we take the chloroform, we're going to put in there 105.595, I think is what the whole thing works out to be, or something like that. Okay. I'll put it in there as 105. 105.5. Okay. Now, what do we know about the water? We assumed that the water was not going into the air, correct? So if that's the case, what should our equilibrium value for it be? 0. Why 0? Because equilibrium value is what? The mole fraction in the gas phase divided by the mole fraction in liquid phase, right? So if the mole fraction in the gas phase is going to be 0, nothing's going into it, I'm going to put in 0 for it. Okay? So that's why I put in an A value of 0 for it. Now what about the air going into the water? We said no, it's not, right? What would its equilibrium value be? 1 over 0, which makes it very, very large, right? Because if I make it very, very large, that means that the air is not going to go into the water. I picked a value of 10 to the 9th. All right, didn't get too crazy because I'm worried about, how the numbers are all going to work out, but I put that value in for it. Now, the rest of these values, we don't care about the temperature dependence on any of these things, so I'm putting in zeros for all of them, and then I have to put in a value for m of 1. So I have, essentially, what I'm going to have is k is equal to a if I do that. Right, so you should enter in all those values. Assume everybody's done that? Yeah, okay, so we're good. Enthalpy, pick something that doesn't require thermodynamic parameters, because you're going to find that for this particular set of components, it doesn't do well for some of the thermodynamic packages. So pick ideal. I think that's fine for it. Physical properties, we can use default models, reactions, there isn't any for us. Now we get into the feeds. Okay, so we have two feeds going into this. I'm going to call feed 1 my water feed. You can go back and look at the column that we have. Feed 1 is coming in the top, so that would be our water feed, right? Goes in at stage 1. Then you have to choose something in here, split or not split. There's no reason, I don't think, for a split on this one. State, temperature, and pressure. The pressure, we were at 2 atmospheres, so that would be 202, 650 in terms of pascals. Temperature was 298.15. Now, for the flows down here, we knew in this case that we had ultimately an L over V value of 132.9. So I'm going to put in 132.9 for the water, and I'm going to put in 1 for the air. And that'll give us that ratio. So let's go to feed 2. Right? Feed 2 is our gas stream coming in the bottom. It's coming in at stage 4. Turns out that you need to specify split below for this one. Okay, split below for this one. Temperature and pressure. Pressure's known, temperature's known. We'll put in 1 for the air flow. And there's a small amount of chloroform in it, and I think we had 100 parts per million going in. So 100 parts per million would be 100 times 10 to the minus 6, or 1 times 10 to the minus 4. Okay. So everybody with me so far on this screen? All right. So let's keep going then. So now that we've got the feeds, go through some specifications, analysis, pressures. We're going to put in constant column pressure, put in the pressure value for it. Heaters, coolers, we're going to assume an adiabatic column, so no heat loss. Efficiencies, we'll assume that they're 1 for the time being. We haven't really accounted for that. Column specs, we have top product, bottom product name. That should be good to go. And so if we've done everything correctly, now we should be able to run this. Now when it comes in and it asks us, it says to verify for us that the feed to stage 1 should be a liquid. Right, that was water and it was a liquid for us, so we can say yes. And then it says that the feed to stage 4 should be a vapor. Yeah, we had air and chloroform, we said yes under those conditions. And it should run, and then we can go and we can look and see what we end up with this. So if everything went well, you should get a screen that looks something like this for the streams. What I want to take a look at here are some of the things like, for instance, say the mole fractions and so on. Because what did we want? If you remember in this problem when we did this, which is a while ago, we were aiming for an amount of chloroform in the outlet airstream of 10 parts per million. Right, so 1 times 10 to the minus 5th. We did this with 4 stages. If we look at what's coming out the top, we're more than 10 parts per million, or almost 12 parts per million coming out the top. We did this with 4 stages. So it suggests to us that we didn't have enough stages to fully accomplish the separation that we wanted. So what we should probably do at this point is to go back and change our operation to make it 5 stages. And do I want to adapt that? Yes. So that just means that I moved the feed stage appropriately for us. If we rerun this, yeah, it's going to do the liquid and vapor checks, and we're okay with that. now when we look at our system, we see that coming out the top, we're now at less than 10 parts per million. So we're between 8 and 9 parts per million coming out the top. So we would be achieving the appropriate separation, in this case, with 5 stages. So you could use ChemSep to solve a problem like this with an absorber or a stripper. Because in either case, it looks like, in some sense, part of a distillation column, really, when you get down to it. And so you can get, various pieces of other information in terms of mole fractions on each of the stages and those kinds of things, as you usually could. But hopefully walking through this example, you can see how you can use something like ChemSep to do something like that. Okay? All right. So any questions, comments about using ChemSep?
I failed to obtain a new step.
I think I missed the last column for the K values.
Okay, so let's come back. Okay, we'll go back. I'll take a quick look at that. All right. So let's do a double check. So you had a problem converging, is that right? The solution converging. Let's just double check some numbers that you have in there then. How about double checking these ones to begin with? You good on that one? Kelsey, how about you? Then let's take a look at, how about the feeds? All right, so if we're good there, I mean, how about like the column pressure? Heat. Good. Efficiency should be at 1. Column spec should be okay. So you're good there. All right, how about components you were good with to begin with? Operation. Okay. Rerun it again, because I'm sure there's probably Did it run?
Failed to obtain a new step reported.
My guess is, I mean, I don't know for a fact. You double checked the thermodynamic table, right? And you have 1s over here for everything in the last column for the M values, 0s for everything in between, and you have the correct.
I entered water then, chloroform then air, so my water value. Okay.
That may do it. Try that and see if it works. Okay, it converged and you ran. Good. All right. So we should be good to go then with everything there. All right. Okay. So I think this wraps us up for absorbers. We're going to finish out the semester looking at liquid-liquid extraction, and then we'll jump into looking at washing and leaching and some other topics. So we're going to take a look at chapters 13 and 14. We won't cover everything in those chapters. Chapter 13 is actually a long chapter, but we'll cover some significant parts of it here. Okay. So because I forgot to put out there slides for you, let me go ahead and do that. For you. Let me just okay, so you should have available chapter 13A slides for you. Okay. So chapter 13, liquid-liquid extraction. Another form of separation that's used quite frequently. We've already looked a lot at distillation, right? We started with flash distillation. We looked at column distillations. We've looked at absorption now. Now we're looking at liquid-liquid extraction. If we're separating liquids, we can separate them depending upon their physical or chemical properties. Right, so if we do a flash type distillation, we're separating ultimately a vapor and a liquid, right? Same way in a regular distillation system. When we come to extraction, particularly when we're talking here about liquid-liquid extraction, we've got a stream which comes in which there's some sort of a solute, let's say. It's in a liquid stream. And we're now going to contact it with a second liquid stream. We're going to allow mass transfer to occur such that the solute wants to move from the liquid it's coming in to the liquid that you're adding. And now you're going to separate out those two streams. That's the general idea. Many of you have already carried out these kinds of operations in some sort of chemistry lab, right? You've used some sort of separatory funnel, right? Sep funnels, mix two liquids, they were immiscible, you let them give it some time to settle, right? You had two separate liquids in there, you draw off the one liquid very carefully, so you separate them out, right? That's a way of separating. That general idea is going to apply here when we deal with liquid-liquid extractions, of course. So what do we end up with? Typically, we're going to end up with two different phases. The phases in this time are going to be two separate liquid phases that don't want to particularly mix, or at least completely mix with each other. The nice thing about doing liquid-liquid extraction is that, generally speaking, we can do this at lower temperatures than we can distillation operations. And that means that we can start to think about separating molecules that are very fragile, heat sensitive, for instance. So certainly this kind of separation process is good for biomolecules, right? Proteins, DNAs, for instance, but it doesn't have to be those. It can be any kind of chemical system in which we can carry out a separation between two different liquid phases. Okay, so that's generally where we're headed for with this. When we carry out liquid-liquid extraction, we're going to start simple. We'll think of, say, a simple single stage, maybe a batch type system. We are concerned about miscibilities of the liquids that we're using. All right, so our terminology here, if we use the term miscible, that means that effectively that we're only going to have one liquid phase under all conditions that we're treating, all concentrations, for instance. Partially miscible systems, which we will sometimes treat, means that there are certain concentration ranges in which there will either be one phase or there will be two phases. And then we have systems which are completely immiscible, which means that there are always two phases, no matter what the concentrations are. Okay. So we're going to consider here, let's say, a mixture of two liquids, let's say A and B, at some given temperature, and now we're going to add a third liquid to it. When we add that third liquid to it, particularly if we're going to do these liquid-liquid extractions, we're going to be looking for the existence of another liquid phase that's going to exist in that system. It could be partially miscible or it could be immiscible. That's going to enable us to separate, let's say, one component, let's say A, from B that was in our original feed stream. All right, so that's the general idea. Let's consider an example here. For our example, let's consider extraction of acetone from water. So we're going to start with a system here. Let's say that we have 200 cubic centimeters of acetone water mixture that contains 10 weight % acetone. And we're going to mix that with 400 cubic centimeters of chloroform. We're going to do this at room temperature, 25 degrees C. We mix them up and then we allow it to settle. In this case, we're going to find that we have two phases that exist in this problem. And so the problem that we're going to ask here is, what percentage of the acetone is transferred from the water to the chloroform? We're going to assume that the chloroform and the water are immiscible in this case, and we're given some densities. Anytime we deal with these liquid-liquid extraction type problems, there's some terminology that we're going to use, and we'll use this consistently. So I think this is important, and we'll use this example to kind of illustrate it. We have a solute. That's what we're transferring from one liquid phase to the other liquid phase. In this case, it's the acetone. We have something that we call the diluent. The diluent, in this case, is what was in the original feed, right? So that was our acetone water feed. It's going to be the water. Then we have our solvent. The solvent is going to be what we're transferring our solute from and then into, right? So the solvent in this case is going to be chloroform because we're trying to move the acetone from the water to the chloroform. The chloroform is our solvent. Then we have another term here that we call the raffinate. So what is the raffinate? It's the exiting stream with the high concentration of the diluent. In our case, the diluent was the water. So the water stream that exits our separation process is going to be called the raffinate. Then we have what we call the extract. The extract is the stream with the high concentration of the solvent. In this case, it's going to be the chloroform stream that we're going to take off after carrying out the separation process. All right, so we've got solute, diluent, solvent, raffinate, and extract. We've got to keep all those straight while we're doing a liquid-liquid extraction problem. All right, so for this problem, we were given, I can't back up, hang on. We were given volumes, and yet of the materials that we were putting in and mixing together, but we were given weight fractions to deal with. Okay? So let's take the density data first, and we'll use it. One of the first things that we need then is we need to know what is the density of our acetone water mixture, given the densities of both the acetone and the water separately. All right, so let's go ahead and calculate that. How do we do that? if you want to know, let's say we want to, let me just get my pen working here. We want to estimate wow, pen is not working here. Sorry, let me see here. We want to estimate the density of the acetone water mixture. Okay. How do we do that? We know weight fractions and we know densities. One simple way of thinking about this would be, we know the densities in terms of grams per cubic centimeter. We could assume that we have 1 gram of material. Then immediately we know how much acetone we have and how much water we have. We can figure out the volumes of each of those separately, sum them up, right? Assume that they add together. And then we can figure out the overall density. So that becomes something like this. Becomes, we'll say, rho bar looks something like 1 over x sub a for acetone over rho sub a. That'll give us the volume occupied by the acetone over x sub w divided by rho sub w. That'll give us the volume of the water. Add those two volumes together, gives us total volume divided into 1. And so we can go ahead and plug in values. We've got 1 over, we had 0.1, 10 weight percent, acetone density 0.792, plus 0.9 over, we're given a density of 1 for the water. And this would give us, I should probably put in some units on here, the units this way. Should give us then ultimately here grams per cubic centimeter, and this is equal to 0.974 grams per cubic centimeter. In that way, then we can calculate the mass of the feed, right? Because we had 200 cubic centimeters times our density, 974 grams per cubic centimeter, and that gives us 195 grams. And we can figure out the mass of the chloroform. We had 400 cubic centimeters, and we had a density of the chloroform of 1.489 grams per cubic centimeter, and that gives us 596 grams. Okay, so now we know the masses for this problem. We're running out of time today, but just based upon the densities that we're given here, if we carry out this separation process, we're going to get 2 liquid layers, a water layer and a chloroform layer, right? Which one's going to be on top? Water layer, right? Has a lot lower density than does the chloroform. Chloroform is much more dense material, right? So when they separate for immiscible, chloroform is going to be on the bottom, water is going to be on the top. Okay. All right. We'll finish up this problem on Wednesday and continue on with liquid-liquid extraction. So have a good rest of your day today, and we'll see you then.